So Theo and I are both working at Planning Space, and in a nutshell, what we're doing is we're building some kind of explainable answer engine, where the idea is that you have a query coming in, and you want to answer that query, taking into account uncertainty, and so essentially returning distribution over possible answers ranked by decreasing probability. To do that, we actually synthesize a whole function in the middle. So essentially, we have a query, and then we assemble a Julia function in a Julia module to be able to answer that query using different bits of knowledge that our system knows about. And then we run that probabilistically to then obtain the distribution that we want to return to the user. The idea is that then it's fully transparent, because as we synthesize a whole procedure, we can actually also return that function so that the user knows all of the steps that were needed to derive the answer. But to do that, we typically need to generate some code. We want to generate a Julia function, a Julia module. So essentially, so it's not just a single function. It's essentially you generate a bunch of types, a bunch of functions, one of which is the entry point that we run to try to answer a query. So in the code generation process, we need to think about, okay, what type of code are we going to generate? And we know about type stable code, and we know that it's a good thing, a good standard practice in Julia, because it makes things more performant. In a nutshell, it is a property of a program where the compiler can reason about intermediate values in your program and know exactly what different types these values have. Then it can do more optimizations, and it is not needed at runtime to figure out, oh, what did we actually get? It is notably named in reference to the notion of type instability, where if at some point in your program some value has an unknown type, then anything that uses that value will also have an unknown type. So it kind of have a cascading effect. So it's apparently better for performance, so why not? Let's go and use it. So first we're going to emit a bunch of types, which would be sort of analogous to what we're doing. So here, let's say we want to answer the query, what is the coolest animal? For that, we're going to generate a bunch of animals as types. And the idea is that here we really generate types, because then we can use multiple dispatch to express the logic. So for example, we can define coolness methods on different types of animals, depending on their attributes. We can be very opinionated and choose that one animal is coolest over all the others. Why not? So then how do we go about typically kind of answering the question, what is the coolest animal? So we're going to do it maybe in a bit of a convoluted way, but it actually represents more what the kind of execution we would be doing in our probabilistic setting. So here we're going to draw a certain number of samples. So we're going to call our generated program a certain number of times. Let's say here 200 times. So essentially, it will involve drawing 2 random animals, in this case. Why not? Then we see which one is the coolest among those 2. And then we're going to record which animal kind of won the coolest battle out of both, and just increment a counter in a dictionary. We also, why not record it in a trace? Because typically, in a probabilistic programming setting, you would record certain results of outcomes in a trace. So, okay, we can do that. And then we take the animal that won the most coolest battles. Why not to say that it is the coolest animal? So obviously, we have a system where latency is very important. We don't want the user to wait for 30 seconds before having an answer to his query. So let's try the performance a bit. We see that we have about 10 seconds for just the first run, about the same for the second. For this kind of example, it's really atrocious. Most of it is compilation time. So maybe we can do something about it here. And actually, when we take a look at it, we see that we have places where we actually involve the compilation of methods where we have actually pairs of animals that need to be compiled. So here, say we have 100 types of different animals. Make it squared if you need to compile methods for possibilities of pairs of them. And we can actually see that with Snoop compile. We see that it shows up. We do indeed compile a lot of methods with these tuples or combinations going on. So now I'll hand it over to Theo and hope that we have an actual solution to solve this.
Yeah, so the first approach we can think of is to tell the compiler, do not do that. and add a no specialize, use a no specialize macro. So the no specialize is going to tell the compiler, do not create a new function instance for each of the types you meet, just make one for this abstract type. And it doesn't help that much, as you can see. We still get around 10 seconds. And when looking on more runs, we actually get worse performance. And one of the main reasons for that is that not specialize only applies on one layer. So it will not propagate through the function that you call. So if you call not specialize on some external functions, then the next time you need to compile, the next time you call an inner function, it's going to be compiled and you get the same problem again. So on higher order functions like map, for-del broadcast, you're going to get all this inner machinery, which is going to create tons of methods. And also, you cannot apply it on things you don't own, right? You cannot go onto the dictionary package and say, don't specialize that. Well, at least it's not possible right now. One solution we propose is to use a wrapper. So we basically create a struct with an inner field, beast, which represents our animal. And you can notice that this is not parameterized. We cannot know in advance what is inside the animal. But all we care about in the end is the coolness. So we only need to unwrap what's inside when we need to compute the coolness of an animal. And this is type unstable, because anytime we're going to call animal.beast, the compiler doesn't know what is inside. And it's going to, so the whole time, basically, when we're going to run our program, the compiler will just program things for animal, not knowing what's inside, and it's going to be fine. It's only when I'm going to call coolness that is going to need to unwrap it, be type unstable, but that's just one small part of the whole pipeline. So let's look at what's happening when we run our same benchmarks. On the first execution, we already get like a 15 times speed up. And you could think, okay, sure, but then you have this type instability every call. Well, actually, it's not even true, because on further runs, it's even faster. Because once we have compiled things for animal, we don't need to redo it again. We just have the performance decrease from the type instability, but which is negligible compared to all the compile time we have. So for our use case, it's especially useful. So we have thought of other cases where this happens. A typical one is the tree, where if you want something very type stable for unhomogeneous nodes, you would need to parameterize the children, the node based on the children, but then you would be parameterized on the children of the children, and you might end up with like this kind of massive parameterized types, for which you would need to compile a new method every time. Another case is obviously our generated type. This is kind of what we showed here. We even found another case in package.jl where there was a pull request to propose to wrap IO, which is an abstract type, and has the same issue that you need to combine all possible IO types with all possible objects that you want to print. And this creates, again, this like massive compilation overhead, which might not be necessary in package where you just care about the first run mostly. So is this bad? Yes, we do not get what we want right now. But it's only some part of the code. We showed a minimum working example for a very specific case. The rest of the code we have is at least aimed at being type stable and work. And I mean, it just shows that Julia is just very easy to control. You can have places where you have a full control over inference, and you can have your static language style performance, and other places you just have the flexibility of a dynamic language. As said, we offer you have some references. And as said, we're from Planning Space, so don't hesitate to talk to us about the project we are hiring. And yeah, thank you. And any questions?